not too bad. Okay, so last time we did a bit of logistics, and then the main idea that you should keep in mind as we proceed with PCAM, that it's really the study of change, okay? How does change happen? If change happens at all, so if you have A, will A change into B? These are the type of questions you want to answer. So the type of those of you who are biochemistry majors, for example, you might be interested in asking whether a protein is going to stay in a folded state or in unfolded state, right? That's an important question. In coronavirus, in the spike protein, we all read about how there is a part of the protein that moves, and it's quite important, whether it stays in or stays out, right? So it's really a question of what changes can happen and if they will happen. And when we go to kinetics, we study about when will the changes happen. So more generally speaking, chemistry itself is a study of change, right? If you want to be philosophical about it, right? That's what chemistry does. It tells you how to change A to B. I mean, that was the whole idea behind alchemy. And PChem is going to apply the laws of physics to study these changes. So when I say laws of physics, yes, the last time, I'm going to sit down if you don't mind. The last time we spoke about classical laws of physics and quantum laws of physics. In 481, we are entirely going to do classical laws of physics, which means force is equal to mass times acceleration. And when we think force is equal to mass times acceleration, we can imagine, for example, a box. And in this box, let's say we have lots of little gas particles randomly moving around, okay? So the very interesting thing is, it looks blue, right, over there? Is it blue? Here it's red. Huh. Color inverted. Yeah. How many of you know what's a Fourier transform? Some of you know. Did you know that when we hear something as you're listening to me, your ears are doing a Fourier transform of what I'm speaking? And then your brain is doing an inverse Fourier transform. So, which is kind of funky if you think about it. But anyway, let's get back to PChem. So the idea here is that if you have a box, let's imagine this box filled up of molecules, okay? These could be just argon atoms, or these could be complicated caffeine molecules moving around, water molecules, proteins, whatever it is. So in principle, we could study how they are connected to each other, how they talk to each other, right? In physics, the simplest model of having things talk to each other is through a spring, right? If you bring it too close, it says, no, too close, goes back. And if you stretch it too far, it says, no, too far, come back. That's one model, but there can be even simpler model. So the spring is one model through which you can interact atoms. Most of the times in PChem, what we are going to do is to go to an even simpler model where atoms don't really talk to each other, except they cannot sit on top of each other. So it's like all of you coming to the class, you don't know who everyone else is. You don't want to know who everyone else is, except, where's Katya? Here. Except Katya is not gonna sit on, let's say, her head. Okay, if that happens, she goes like, no, go away. Okay, that's the only interaction. So this molecule this particle over here cannot go and sit on top of this molecule. So this is called an ideal gas. But things are really, really tiny. They are just moving around blissfully, unaware of each other's existence, except when they collide. When they collide, they go like, nope, this is not going to happen, and they go back. So this model is called the ideal gas or perfect gas. And today we are going to write down the exact criteria for what constitutes an ideal gas or a perfect gas. But for now, before we do that, we have to think about, so I said chemistry is the study of change, and physical chemistry is the use of physics to study change in chemistry, right? But before we get into how change happens, we have to think about how do we describe this system, right? I just drew a bunch of molecules in a box. Now my question for you is, can we be more quantitative about defining the state of this system? What are the descriptions or parameters that you would use to describe this state of the system? So what do I mean? For example, you could say, I am hungry right now, or I am thirsty right now, right? So for this system, if you have a bunch of molecules in a box, can you think of what are the variables that you would use to describe the system on a whole? Any ideas? Go ahead. Pressure, perfect. Number one is pressure. What else? Volume, exactly, because the box could be smaller, box could be bigger, right? You could all be packed into a very tiny classroom and it would be not very nice. What else? Temperature and something else? Huh? Number of moles, perfect. So in number of moles, you have to remember that if this was made up of gas molecules of type A and gas molecules of type B and gas molecules of type C, then we would have to talk about number of moles of A and B and C separately, right? But for a long time in physical chemistry, maybe till the 60% of the semester, we are going to study systems which are made up of only one type of particle. Okay, so we will just say N. We will not talk about Na or Nb or things like that. Okay, so these four variables turn out are sufficient to describe the thermodynamic state of a system. These variables are called variables of state or state variables. Variables or state variables. And using these four, you can describe a system in full thermodynamic detail. So you might ask, why these four? Why not a fifth one? Why don't you need a sixth one? There is some, in graduate thermodynamics, if you take 684, you will study as to why four is sufficient. And actually in a little bit, we will see that you don't even need four. You just need three of them. Anytime you have three of them, you can figure out the fourth one using something such as the ideal gas law, for example, right? So these four are the variables of state, which are our really starting point for the study of physical chemistry. Now, out of these four variables, two of them are kind of very easy to understand. I would argue that the volume of the box and the number of molecules in the box are really easy to understand, right? You just look at the box and you count number of molecules that are over there. That's simple. Volume, well, you just measure the volume of the box. Of course, the box could be not cubic, right? The box could have some bizarre shape and then you have to worry about shape of the box, but let's say the cubic box. Pressure and temperature are a bit complicated, okay? So let's take, so the point I'm making here is that temperature and N are easy to understand. Pressure and volume are trickier. And we, sorry, what did I say? Volume and number are easier to understand. Pressure and temperature are trickier. And it turns out that actually both of them are coming due to the same fundamental origin. Both pressure and temperature are happening due to the movement of the gas molecules. So let me ask you a question. If you took this box of gas molecules to 0 Kelvin, to absolute zero, what would be the temperature of the box? Zero. I just said it took it to absolute zero. But what would be the pressure of the box? Why?
Because the pressure is the amount of force in the fluid.
Yeah, exactly. So pressure measures, like I said, is when you have gas molecules in the box, they are constantly in a state of movement, right? So you all came to class, you had a lot of coffee or Red Bull or whatever, you're just moving around. And in this random motion, you go and hit against the walls every once in a while. And the force divided by area that you apply as you hit on the walls is the pressure. So if there is no movement, there is no pressure. So at 0 Kelvin, temperature is zero, pressure is zero. Does this mean that temperature and pressure increase linearly? They don't. They increase the same way. At zero temperature, pressure is also zero, but it does not mean that the temperature versus pressure profile is linear. They are both related to movement. Let's see how exactly they are related to movement. So let's first talk about pressure. By the way, at any point, please interrupt me if you have a question. It gives me a chance to get a sip of water, and it makes sure to me that you are actually not asleep. So the molecules in our box are constantly bombarding against each other, right? They bombard against each other and say, go away. And the same thing, they bombard against the wall. And every time they bombard against the wall, they come back. And this bombardment is what leads to the pressure. So, and pressure, if you remember any physics, pressure is defined as force by area, right? And what is force? Force is rate of change of momentum, right? Force is rate of change of momentum by area. So therefore, pressure is proportional to the change in velocity of the gas particles as they go and bombard against the wall. And you can see how quickly I'm starting to sneak in a little bit of calculus, right? Delta is the notion in calculus that we use to measure the change in velocity. So pressure, and it's of course related to the mass of the gas particles, and everything. And you have to, so approximately it's proportional to the rate of change of velocity. And so if you have, let's imagine a container where you have a movable wall in the middle. So this is a movable wall. And let's say you have gas at high pressure over here. The wall is movable, but gas cannot go through it, okay? It's not porous. It can just slide back and forth. It can do this back and forth motion, but gas cannot go through it. And you have gas at low pressure over here. What will happen to this movable wall? Which way will it move? Who thinks it will move to the right? Who thinks it will move to the left? Okay, no one at least thinks it will move to the left. Most of you think it will move to the right, and some of you are sleepy. That's okay. So why will it move to the right? You answered many questions. Yeah. But I imagine that's what you were also going to say. So it's a high rate of collision, right? You're applying more force per area. So high pressure means higher force per area. Low pressure means lower force per area, right? So you are experiencing more force from the left side, and this thing will keep moving it to the right. How long will it move? Will the movable wall go to the very end of the container, or will it stop? You're nodding your head. When do you think will it stop?
Because when the wall moves to the right, the pressure in the volume in the left is decreased, so the pressure decreases.
Exactly. So absolutely correct. So what he's saying is that as this thing moves to the right, the volume on the left increases, right? So these gas molecules, so let's imagine there were 10 of you in this room and you were in a tiny box, right? So you would be hitting the wall very frequently. But if I put you in a very, very big lecture theater, you would be hitting the wall less frequently, right? So the pressure goes down. As the wall moves to the right, the pressure on the left goes down, and eventually the pressure becomes equal. When pressure becomes equal, you reach a very, very special state. This state is the state of mechanical equilibrium. Pressure becomes equal on both sides, okay? So that's mechanical equilibrium. So this is pressure. I mean, it's not that complicated, but we just took a slightly abstract way of looking at it. Any questions about pressure? Okay, let's go to temperature then. So pressure, the take-home point here is that pressure is related to rate of change of momentum per unit area, okay? Temperature, and it comes from gas particles hitting against the wall. So you could have gas particles moving at a certain speed just randomly here and there. And if you double the size of the box, the pressure will go down. Temperature will not go down. Temperature will stay the same. Temperature is not related to how they collide against the wall. Temperature is something slightly different. Temperature, in fact, is related to the kinetic energy of the molecules. And I know my writing is terrible, but this is really to assist, what I'm talking, because it's better than at least when I was teaching it 2 years ago, because on the blackboard, you don't have a copy of whatever was written. So in other words, temperature is proportional to V squared, right? Because that's what kinetic energy is. Kinetic energy is half times mass times velocity squared. And I'm saying proportional because I'm ignoring the mass. I'm saying for the same mass, If you change the velocity, if you double the velocity, the temperature will increase by 4 times. It's a square dependence. So, so pressure is related to the change of momentum. More specifically, it is related to mass times delta V, and temperature is related to mass times V square. Okay, and you also have a half, but I'm talking about proportionality constant. And just like we had mechanical equilibrium, now we can talk about thermal equilibrium. Let's imagine the same container. And now our wall in the middle allows heat to go back and forth. Okay, the wall won't move. It's a rigid wall. It cannot physically move, but it allows, wall allows flow of heat. And let's say here we have hot at temperature T2. I just remembered we have a color inversion on that, but in the notes, so this is a bit of a mind trip because I would have used red for the hot, but now you see blue. So if I try to invert it, then you go back to my notes, you will see blue for the hot. So I'm not going to try. And you have cold here for T1. So just like the wall moved until the pressure becomes equal, here heat will move. And as heat moves, you're drawing kinetic energy out of the left and pushing it to the right side, right? And this will happen. So heat flows from left to right until temperature T1 becomes equal to T2. And this is also a type of equilibrium. This is called thermal equilibrium. Right? Now you could imagine a wall which allows heat to go through, and the wall itself can also move. So now you will reach equilibrium when both thermal and mechanical equilibrium, both of them have to happen. Can we think of other equilibriums on the basis of these 4 variables of state? Anyone? You can also answer, it's okay. You can't think of any? Anyone? Your hint is N. Can N reach to a certain type of equilibrium? Not in a single component system. Or actually even in a, yeah, it would be chemical equilibrium, right? When you have too many of things in a certain side and too few of those things on the right side, it will try to go away and equilibrate. And we'll talk about chemical equilibrium later. Chemical equilibrium does not matter right now because we're talking about one component system. When we go, maybe second half of the semester, we will talk a lot about chemical equilibrium. But right now we are interested in mechanical equilibrium, which is when the pressure becomes equal, and thermal equilibrium, which is when temperature becomes equal. So one of the most simple yet profound things about thermodynamics is that even though I wrote down that a system needs 4 variables of states to describe it, it turns out that you don't need 4, you only need 3. Turns out, if you know any 3 of pressure, temperature, volume, number, you can calculate the 4th. And I'm going to write down something after this, which is super important. And sometimes when you read books, it does not sink in your mind. It definitely took a while when I was an undergrad to sink in my head. This is true under equilibrium. If you're out of equilibrium, this is not going to be true. What does it mean? It means that when I drew this container, okay, and you have high pressure on the left side and you have low pressure on the right side, and your wall is still moving, then you're out of equilibrium, right? Things are still moving. It's like all of you are still entering the classroom, but now you're in a state of equilibrium. Equilibrium is not death. Equilibrium means that heat is still going from left to right, but the same amount of heat is coming from right to left on an average, okay? So equilibrium, living systems can be in equilibrium, but that does not mean living systems are dead. No, equilibrium is just balance of things, right? So Under equilibrium, which is when the pressure has become equal or the temperature has become equal, under equilibrium, you don't need all 4 of the variables. If you knew 3 of the variables, you can identify the 4th variable. And this is actually quite profound. The reason I think it's profound is because this happens because equilibrium is in a certain way a constraint on a system. Those of you who are mathematically inclined would remember that anytime you add constraints to the system, the number of free variables that you have in order to characterize the system go down. You know what I'm talking about? If I draw you a straight line, right? So this is X and this is Y. And I give you an equation of a straight line, right? You can be anywhere along this line. Now I give you a constraint. I tell you X must be equal to 1. So suddenly, if you're moving along this line, you have 1 degree of freedom that you can matter, right? That you can vary. But anytime I tell you that X must be equal to 1, suddenly this is the only solution that is possible. If you know X, you know Y, right? So constraints reduce the number of free parameters in the system, and equilibrium is a constraint. It's a good constraint, but it's a constraint. This happens because equilibrium is a constraint on the system. Okay, so anytime you apply the constraint, any constraint on a system, in the state of equilibrium, the number of variables go down, and overall equilibrium is 1 constraint. So it means that it reduces the number of variables by 1. This is an abstract way of thinking about it. What this practically means that we can always write, again, under equilibrium, and I will keep mentioning under equilibrium because when we get to start talking about entropy a few weeks from now, you will see how we often go out of equilibrium, and that's when it will matter. So we can always write down pressure as a function of temperature, volume, number under equilibrium. We can also write down volume as a function of temperature, pressure, number under equilibrium. Or we could write down temperature as a function of temperature, pressure, volume, number. These type of equations are quite important and they have a name. They are called equations of state. So, and these equations of state are super, super important. Have any of you seen an equation of state before? You have to have if you're taking the prerequisites for this class. Go ahead. Which one? PV is equal to nRT, the ideal gas law, right? So later we are going to show that if you have a gas, if you approximate your system as made up of gas molecules that move oblivious of each other, and the only thing they cannot do is to sit on top of each other, that leads to an equation of state given by PV is equal to nRT. So for example, PV is equal to nRT is an equation of state. I am gonna abbreviate it as EOS, okay, equation of state. So this EOS term, equation of state, I'm just going to abbreviate as EOS. So which means that pressure can always be calculated as nRT by V. This is one example. Do we know other equations of state? Anyone remembers? It starts with a V. You're thinking hard. Maybe something's coming to your head. No? All right. Van der Waals equation of state. So Van der Waals equation of state goes one step further than this one, and it says that, so in the perfect gas, these particles not just cannot sit on top of each other, they are also very, very tiny. If you start giving them a finite volume, you will reach to Van der Waals equation of state, and we'll look at that later. For now, let's just talk about the perfect gas equation of state. So this equation of state By the way, for these classes, I'm mirroring Atkins quite closely. So if anything is confusing, you can, of course, I think the recording is working today also. You can go and look at the recording and you can also follow Atkins. I'm mirroring Atkins quite closely. So it should help you if you get confused, but hopefully not. So this is our ideal gas law or ideal gas equation of state or perfect gas equation of state. So it applies to ideal gases. What do I mean by ideal gases? So ideal gases really mean that, let me just draw a 2D box. I won't draw a 3D box just for simplicity. That let's say you have particles in this box. And let's say the distance between any two particles is A. Okay, A is going to change, right? The particles are moving all the time. Let's say at any one instant, the distance between two particles is A. So I'm trying to write down for you what is the definition of an ideal gas. So the first important thing is that gas particles are indistinguishable hard spheres of radius r. So this indistinguishability itself is a big approximation, right? Clearly, all of you are distinguishable. Even with your masks on, I can tell who is who, right? But in classical, here we are assuming that they are all indistinguishable. They are really basically the same. We don't care which one is which one. We could go and tag one of them using some nuclear, we could make an isotope or something like that. But for all practical purposes, we assume they are indistinguishable. And they have a radius r. What do I mean by radius r? Which means that you could go and look at it through a lens. If you look at it through a magnifying lens, you will see that this thing actually has a radius r. Okay, it is a sphere, but it's a very, very tiny sphere. So how tiny? How do we define tiny? Tiny enough that r at any point of time is much smaller than a. Okay, so we imagine all of us are like little spheres, like M&Ms or whatever. M&M is not a sphere. What's this, by the way? I thought it might be a box of M&Ms. It's not. So let's say we are all spheres of radius r, but the distance between any two spheres is so large. A is very large compared to r. Okay, this is another approximation. So most of the times we don't see each other. The number of times collisions will happen will be very, very small. Will not be too many. So that's the second assumption. The third assumption is that molecules or particles are constantly moving in random directions as per Newton's laws. What do I mean by Newton's law? F is equal to ma. Basically, force is equal to mass time acceleration is causing them to move every once in a while. How do they get acceleration? It's like you set them off to keep moving and there is nothing to drag them. So they will keep moving. Every once in a while, they will collide and they will go back elastically in the opposite direction. Okay, so this is how they keep moving. Every once in a while, they collide elastically. Anyone here remembers what's an elastic collision as opposed to an inelastic collision? Go ahead.
All the energy is reserved.
Okay.
It stays before and after.
Yeah. And so what happens in an inelastic collision? Lost. And most collisions will be an elastic collision, right? If I go and collide against her, we'll probably get little bruises on our head. Some energy will go away. So it's a very fake model. It's not going to happen. What kind of a chemical system? Oh, okay, let me write down the fifth one, and then I want to give you a bit intuition into where this might apply. No forces between particles except when they collide. These are the 5 conditions that define an ideal gas or a perfect gas. Can you think of a chemical system where this might be close to getting true? Any ideas? People in the back. What's your name? Say again? Okay. Can you think of a system? Would it, let me ask you this way. Would you expect this to be more true for argon or for caffeine? Why? It's a noble gas, right? It doesn't like to react. It doesn't like to interact with anything. Caffeine is also bigger. It's got many, many things going on. Yes, you're absolutely correct. For noble gases, you expect this to get more and more true. But even, and noble gases don't have electrons hanging out, right? That's the other thing about argon. You don't have electrons in like S electrons, which are just out there, which are going to do funky things. It's just boring. So boring particles will follow this. But even argon has a finite size. So if you try to measure the pressure versus volume for argon as a function of temperature, even for argon, you won't find ideal gas to be true. You will see deviations. It will become more and more true as you go to higher and higher temperature. Do you see why this will become more true for higher temperature and not at lower temperature? Go ahead. Even simpler, what happens to the volume as the temperature increases? Things expand, right? So things become further and further and further. So as you increase the volume, this condition becomes more and more true. As you increase the volume of a box, let's say you and I are sitting in this classroom and the classroom becomes 10 times, 20 times, 40 times bigger. So the probability that we come and collide with each other just keeps going down. So as you increase the volume or as you increase the temperature, the ideal gas law becomes more and more accurate. So it turns out that using these 5 assumptions, you can actually sit with pen and paper, start with Newton's law of motion. You can write down force is equal to mass times acceleration, and you can derive PV is equal to nRT. It's not easy. I'm not going to do it in this class. This is really the subject matter for like one of the graduate classes. If any of you is interested, send me a message on Slack and we'll post how it is done as an advanced reading material on the Slack channel so you can go and read it. But you have to take my word for it that given these 5 conditions, we can derive PV is equal to nRT. I'm not going to do that derivation in the class because we have to get this class. It's not just about math. We have to get intuition for things. That's what this class is really about. So I will skip this derivation. The reason I still wrote down these equations is because not today's class, but the next time I'm going to use these 5 properties and the ideal gas law to show you why temperature is actually proportional to V square. Where does it come from? So intuitively, you can see, right? Kinetic energy is proportional to temperature. If things have a lot of kinetic energy, the temperature goes up. But next time you will see that it is exactly true. Using these 5 equations and PV is equal to nRT, we can derive that temperature is indeed proportional to velocity squared. But the ideal gas law, so in order to do all this, we have to really believe something. We have to believe something that you all take for granted. I take for granted, and people have taken for granted for maybe the last 90 years. Namely, that things are made up of atoms. Believe it or not, until 1910 or 1905, this was hugely controversial. The atomic view of matter or chemicals was not believed upon. It was not agreed upon. In fact, in Germany, it was so controversial that the guy who really started thinking about all of these things very carefully, his name was Boltzmann. Some of you might have heard his name. Has anyone here been to Vienna? No one? No one's been to Vienna? You have been to Vienna. So next time you go to Vienna, go check out the graveyard in Vienna, the big one. And they have Boltzmann's grave over there next to Mozart and Beethoven's grave with his face looking very, very angry. The reason he was so angry because he was trying to come up with physics and chemistry on this idea that things are really made up of atoms. And he did beautiful work. But in Germany and in the rest of the world, his ideas were so controversial, no one believed him, and eventually he hung himself and committed suicide. It was so controversial to think that things are made up of atoms. People thought everything is ether, it's fluid. And so we take this for granted, but until 1905, 1910, it was not taken for granted. And in 1905, of course, Albert Einstein came, right? Who showed like, look, this is crap. It is really, really true. This is the picture. And he used it to show such important things that people had to stop and go like, okay, maybe you are right. And then in 20 years later, or 30 years later, people were actually finding the oil drop experiment and things like that. You must have studied in your high school chemistry, right? People were actually starting to see that there is something like an electron or something. So in those 30, 40 years, science made extremely rapid progress. Some sort of bad progress also, right? Because in 1945, we had nuclear bombs, which were doing damage everywhere. So think about it. In 40 years, how quickly we proceeded, which makes you wonder how much can we proceed in the next 40 years. I mean, it's hard to imagine, right? And it could be anything. So anyway, the reason I went off to this story is to tell you because ideal gas law can be derived by thinking of an ideal gas made up of particles which are indistinguishable, which barely collide with each other, and when they collide, they move elastically. But this PV is equal to nRT has existed way before Boltzmann, way before early 1905, 1910, when people were still arguing over the atomic picture. They were not arguing over the ideal gas law. PV is equal to nRT was still accepted. And the reason it was accepted is because people had derived it empirically, okay? So there was one scientist named Boyle. He had a law named after him where he had shown that volume is proportional to 1 over pressure. If you increase the pressure on something, the volume goes down. Right? He had made this empirical observation. So these were all empirical observations in almost 1700s to 1800s. So Boyle had said that volume is proportional to 1 over pressure. Charles had said that volume is proportional to temperature, or he had found by doing experiment that it is kind of proportional for most things. And Avogadro had said that volume is proportional to number. So if you combine all these things, what do you get? Volume proportional to 1 over pressure multiplied by temperature multiplied by number, right? I just take all three and multiply it together. So what do I get? I get volume proportional to number, temperature divided by pressure, or pressure multiplied by volume proportional to NT, or PV is equal to nRT, where R is gas constant, 8.314 joule per K per mole. So, so when I said these are empirical observations, what does it mean? Let's think about Boyle's law. Boyle's law means that at a given temperature, pressure versus volume looks like this. At T is equal to some temperature T1. Here's the question, and I want you all to think carefully. What would happen at T is equal to T2 more than T1? Will this curve move up or will this curve move down? Any ideas? So should it look, so my question is, should it look like this, which is, let's call it top, or should it look like this, let's call it bottom? As the temperature is increased, does it go to top or bottom? Why?
Temperature is proportional to the product of pressure and volume.
Yeah. So what he's saying here is that the product of pressure and volume is related to temperature, right? So if you increase the temperature, the product of pressure and volume has to go up. So it keeps moving up. So we can just use this black curve at T is equal to T2 more than T1. And these curves are measured at a certain constant temperature. So they are called isotherms. Isotherms. And you can see for most materials, you can measure isotherms like this, a pressure versus volume plot. The reason why these pressure versus volume plots or such isotherms are important later on, and we will see this later in the semester, is let's say you design a funky new molecule, okay? Let's say you design an anti-cancer drug or some protein which can work as an anti-cancer, like a natural drug, some peptide or something. And you don't quite know what are the nature of interactions inside this protein. How does it really interact with something? By measuring this pressure versus volume curve, thermodynamics allows us to go and think about what is the nature of interactions between the gas molecules. For example, if pressure versus volume curve fit this profile perfectly, what can we say about the nature of interactions? It's probably an ideal gas, right? For an ideal gas, we know PV is equal to nRT. So if you're really getting a perfect fit of PV is equal to nRT, you can go back and deduce it is probably closer to something like argon. For a real material, for a real chemical, you will not get that type of a behavior. So a large part of thermodynamics in practice, and actually, and not just in universities, but also in industry, for many of you will go and work in very big, important companies and do industrial research. You make such measurements on some new chemical that you have made, and you go and try to deduce what is the nature of interaction in the chemical itself. And you have to come up with models that can connect everything. So these are isotherms for Boyle's law. Now let's go to Charles' law, which is volume proportional to temperature. Charles's law would mean volume at temperature. How would this look like? Volume versus temperature. Go ahead.
Temperature increase, or decrease.
Okay, so it will be a straight line or a curve? At constant pressure, should it be a straight line or a curve? It should be a straight line. Volume is proportional to temperature. And it should be a straight line going through the origin. So it will look something like this. At pressure is equal to P1. Same question as for Boyle's law. What would happen when I increase the pressure from P1 to P2? Will this curve go, will the curve move anti-clockwise or clockwise? Any ideas? So yeah, exactly. So pressure is the proportionality constant that you see over here, right? N over P. So if you increase the pressure, what happens to N over P? It becomes a smaller number, right? So the slope goes down. So as you increase the pressure, this P is equal to P2 more than P1, the curve starts to go to the down, in a clockwise manner, it goes down. And these curves are called isobars because they're measured at a constant pressure. So, and similarly, you can draw, any questions? Similarly, you can draw an isochore. You can go and read it in Atkins. I'm not going to draw it here, which you measure at a constant temperature. And yeah, you can make, so isobars and isotherms and isochores are things we can measure experimentally. The key point I want to make here is over here, I drew something in 2D, right? Pressure versus volume. Here I drew something in volume versus temperature. Now let's try to think of everything in the same plot. What do I mean by that? And this is going to be a bit of a mind stretch, so stay with me and try to focus. Let's try to think of not just a 2D space, but 3D axis, where I have pressure over here, volume over here, temperature over here. And you have a given material that you can create at any pressure, volume, or temperature. ideal gas law means that for n is equal to 1, let's say you have only 1 mole of this particle. Okay, let's not worry about the number of particles you have. You will be restricted to a surface in this space. Okay. Ideal gas law, or more generally, equation of state, means that in 3D pressure, volume, temperature space, we are restricted to a surface, and this surface is the surface of equilibrium. If you're out of equilibrium, you will be away from the surface, but you would desperately want to come back to equilibrium. You will come back to this surface. Why should it have to be a surface? Because what we have said that PV is equal to nRT, right? And if n is equal to 1 for 1 mole of the gas, PV is equal to RT for 1 mole. So and we can imagine the surface over here, right? But anytime you want to visualize a 3D space, the best thing to do is to go to the corner of the room, okay? So imagine this axis is pressure, the axis going this way is volume, and that axis is temperature. So if you did not have equation of state, you could have pressure, volume, temperature, any 3 values could be possible, right? Because there is no constraint connecting them for n is equal to 1. But anytime you have equilibrium, you know that pressure multiplied by volume must be equal to R multiplied by temperature. So you can no longer be anywhere in this room. You're restricted on a surface. For ideal gas law, the surface will look kind of simple. It will look like a hyperboloid or whatever it's called. For more complicated things, it will look very, very complicated. Any questions about this? We have 1 minute, then we stop for today. Yeah, please. Yeah, so Boyle's law says V is proportional to 1 over pressure, right? So if you increase pressure, the volume goes down. While Charles' law say that volume is proportional to temperature. As you increase temperature, volume goes up. So you have an inverse relation in Boyle's law. While in Charles' law, you have a linear relation. That's why it looks opposite. So my exercise for you is to try to plot the functions y is equal to x and y is equal to 1 over x in Wolfram, Alpha, or Mathematica, wherever, and you see how they look like. And also try to visualize this in 3D. Okay, so next time we are going to talk about the kinetic model and try to connect the temperature to the kinetic energy.